right, hey, so we're going to be talking about speed and velocity in one dimension here. This first example is a pretty simple example about speed, right? I think we're focusing on here. So just a quick, at a Molson Indy race in Toronto, a driver covers a single lap of a distance 2.9 kilometers. They give us an average speed of 1.5 times 10 to the 2 kilometers per hour. We want to know the average speed in meters per second. So this is just a simple unit conversion. And if you've been doing this stuff for a while, you know that converting kilometers per hour into meters per second is just a simple operation of dividing by 3.6, right? And so I'm going to take my 150 kilometers per hour, which is my speed, and I'm going to go ahead and, divide it by 3.6. And that has to do with the fact that there are 100 meters in a kilometer and I said 100. I meant 1,000. And there are 3,600 seconds in an hour. And so after you do some conversions there, that works. And so we end up getting 41.7 meters per second, right? So that's A. So the time in seconds that it takes to complete a lap, okay? Now, since we're talking about completing a lap, we want to be talking about using the speed formula, not necessarily the velocity formula. Because the speed formula, remember, is average speed is the total distance traveled divided by time, change in time. So since we're kind of going around in a circle here, our total distance traveled is going to be the circumference of a circle, and then our total time is what we're looking for. All right, so this is for part B. We're just going to go ahead and use this formula. Speed is equal to distance over time. You can kind of just write it in the simplified version, right, as well. And, well, it looks like we're given the velocity, or the speed, which is 41.7. Let me just get that there. 41.7 meters per second, and we are given the distance traveled, which is 2.9 kilometers. So that's going to be 2,900 meters. So again, we're going to want to put that into meters, and we want to solve for time. So doing a little bit of algebra, we can multiply both sides of the equation by time, canceling each other out, and dividing both sides of the equation by velocity, canceling these out, and we end up with time is equal to distance over speed. I keep saying velocity, but I want to be saying speed in this case, because I'm not using velocity. Remember, velocity is the vector form of speed. And so we're just gonna go ahead and put this in there. 41.7 meters per second over 2,900 meters. Oh, this is pretty convenient. Our meters end up canceling. And my numerator, the units are 1 over seconds, and we end up with a time, okay? And so, oh shoot, I messed this up. Sorry, guys. I've got distance here. I was like, what? Something's going on here. Well, this was a bit of a mess up. I put my distance in the top and well, I messed it up. Most of you, I'm sure. So it's actually this. Here, it's 2,900 meters over 41.7 meters per second. I was wondering why that was happening. My units weren't going to work out. Now I notice my units are per second in the denominator, and a denominator inside of a denominator can be moved to the numerator due to algebra, and my final units become seconds. And if I just go ahead and calculate this, it's going to be 69.6 seconds. Okay. So this is basically just a very simple example for us to be talking about speed. Okay. Now, don't forget, you would also, in a standard physics course, be talking oftentimes at the same time velocity. And so why do we bring them up at the same time? Well, because they're effectively virtually the same formula here. But velocity is the vector format of speed. And rather than doing total distance traveled in the numerator here, let me make it full screen. Rather than doing total distance traveled in the numerator, I'm going to be using displacement. So remember, displacement is how far you move from your starting position to your ending position, your final time. And those two positions are marked by certain times, and those times would be time initial and time final. Okay, so you effectively end up getting a different situation, because if you, for example, move somewhere and then move back to your original position, you would actually have a change in position of 0. And so you could actually have a velocity of 0, even though you did some kind of movement, okay? Because remember, this formula is dependent on not the path that you take, but the change in the two positions, starting and initial and final positions. Whereas the speed formula takes into consideration the path that you take, because this section of the formula is total distance travel regardless of the direction. Okay, so now cyclist here in the above figure takes 25-ish seconds to cover a particular displacement of 115 meters east. Okay, and so from position 1 to position 2. Okay, so here's position 1. Okay, and here's position 2. It looks like my change in position is 115 meters east. That's what we're looking at here. Calculate the cyclist's average velocity in this case. Okay, so I'm just going to go ahead and, wow, this was pretty simple. I'm just going to go ahead and stick these values directly into this equation here. All right, so I'm going to get, for part A here, velocity average is equal to, let's see here, change in position over change in time. And so remembering that my change in position was given here at 115, right? So I'm just going to go ahead and write that down. 115 meters east. I will maintain this direction, divided by the change in time, which was 25.1 seconds. Okay, and our units for this are going to be meters per second, and we're going to maintain a a direction. Remembering, because velocity is a vector due to the fact that it's got a vector symbol there and it's defined as a vector, our velocity is going to be, well, whatever this calculation turns out to be, 4.58 meters per second. And that's east. I'm going to keep with 3 significant digits because it looks like both of our input values are 3, 1, 2, 3, and 1, 2, 3 significant digits. Remembering that the quotient of 2 values, the final result should have no more significant digits than the least significant input value. Okay, well, here we've got part B. If the cyclist maintains the same average velocity for about an hour here, well, an hour, actually pretty close to an hour because we've got some precision, levels of precision here. What is the total displacement? So we're going to want to know now the displacement, which is this variable. And here they're giving us a time. And, well, they're giving us a velocity. Well, where is it? Oh, this velocity. So if the cyclist maintains the same average velocity, which is this one. So in a way, part B, they're just kind of letting us know that, look, oh, got a little bit of something happening there. So part B, there, I have malfunction in my pen. My velocity is going to be the change in position over the change in time. Okay, oops. Let me, this was an A in there. And so what they want to know, what is the total displacement, which is this variable right here. So I'm going to solve for it. I'll just multiply by time on both sides of the equation. So if I multiply by time here and here, my delta t is a delta t, and my delta t there cancel. And so I'm left with change in position, which I forgot the vector symbol here, so let me put that on there. My change in position is equal to my time times my velocity, or I guess I'll just write my velocity times my time, okay? Which is the velocity that they gave us. So they're just telling us, look, this is the same velocity, meters per second east, times a scalar of time, 1 hour. Well, we were saying earlier that 1 hour is equal to 3,600 seconds. So I'm going to go ahead and do that, 3,600 seconds. And if you, again, look closely here, my seconds cancel with those, leaving a meters as my only remaining unit. And boom, that's a displacement, which makes sense. So I'm going to get a final solution here of, I don't know, what's it going to be? 16,500 meters east. Okay. Now we could put that into kilometers, which would be, see, 1,000 kilometers. Wait, is this right? 1, 2, 3, 4. See, I think that's correct. Okay. There we go. Now, if the cyclist turns around at position 2 and travels to position 3, which is, I guess it looks like off the map, which would be, oh no, where is position 3? 565 meters west, which is over, I guess would be over here somewhere. So this would be a different situation. So here they're sitting at position 2. Okay. This is a bit of a strange one. We're interpreting this a bit funny. So my guess is we're starting with position 1, goes to position 2, and then he goes over down here to position 3, which would be back here. Let's just say that position 3 is over here, okay, which is, what is it, 565 meters west, so 565 meters west. We'll call this position 3, okay? And my guess is that the cyclist is sort of, I'm going to draw a little cyclist here, bicycle. I don't know, that wasn't very good, but whatever. There it is. There's my bicycle. So my cyclist started here, went there, and then went back to here. Now, if I asked for the speed of the cyclist, or if we were asking for the speed of the cyclist, we would have to take into consideration the total distance traveled, which would be 115 plus whatever it would take to get back to here, okay? But since we're asking for the velocity here, we only want to consider the starting position and the ending position. So effectively what that means is this motion here, the fact that we turn around and then come back, the motion moving from position 1 to position 2 and then back from position 2 all the way to position 3, well, whatever, these two cancel, these two motions, the forward and the backward. So really we're only counting the motion from here to here. Okay, and so maybe part C I'll do up in this corner since we appear to have some space. And so we want to know the average velocity. So I'm going to, again, just take my average velocity formula and I'm going to put my change in position formula and my change in time. So I'll do, remember my position is final position, or position 3, minus position 1, okay, over my change in time, which is going to be, my change in time is 72 seconds. So this looks pretty simple. So let's go ahead and write position 3 here, which is 565 meters west minus position 1, which is 338 meters west. Okay, so we want to be careful and keep track of these vectors in these directions here. So 72.5 seconds. All right. So as you can kind of see here, both of these are west. So since they're both west, this is a one-dimensional vector subtraction. And so we don't have to overcomplicate it. We can just take 565 and subtract 338, and they keep the direction that they have, okay? And so I end up with, I don't know, what was it going to be? 227, 227 meters west. Okay, oops, my pen is giving me some trouble. It's a sticky pen today. Okay, there, west, over 72.5 seconds. Okay, and that one, I didn't calculate that one out. Well, let me go grab a quick calculator. What's that going to be? 20, about 30, about 3-ish. We're going to go with 3. 3 meters per second west. Okay. Sorry, it should have been a little bit more detailed than that, but I forgot to calculate that one out beforehand. So it's like 3 point something or other, because 21 divided by 7 would be 3. This is 22-ish, whatever. So we're talking 3. Okay. So anyway, that's a little bit of a recap on velocities. and speeds. All right.